So I will talk a bit more in general about this whole issue of intelligence and have this question: how much intelligence is there in artificial intelligence? I will talk a little bit about logical reasoning, but this will be a bit more general talk. I'm Han van der Maas. I'm a professor at the Psychological Methods department. I'm also an external faculty member at the Santa Fe Institute. And it's interesting to measure to tell that the whole start of AI has a lot to do with chess, and I will talk a lot about chess actually also in this talk. And a famous dissertation written by A.D. de Groot a long time ago was about thought and choice in chess, and that was one of the starting points of current AI. And A.D. de Groot was also the one who started our group. I'm actually his successor in that sense, and it's always good to mention this. And I will talk a bit more about chess later in the talk. So my talk is this. I will first say a few words about the philosophy of AI, then a short history about intelligence, how it is studied in psychology and what it means. Then a short history about the role of chess in AI. Some observations about the current relation between AI and psychology in relationship to intelligence, and then come back to this main question about true intelligence. And this paper is, my talk is mainly based on a paper I wrote with Claire Stevenson, who's sitting here. I do all this work with Claire, and we wrote a paper 5 years ago. So this now is a new update. And this was an update of an earlier paper by Roger Schenk in 1980 with the same title. And it's very interesting to read his paper, which was written in 1980 about the same question and how he thought about AI at that point in time. We tried to write an update, and this is my most recent update, is giving this talk. Part one is about the philosophy of AI. I don't know how many philosophers are here, but I now realize it's only one slide. Sorry. But I will come back to philosophy later on. The slide is actually this slide, and most of you know this, although maybe not this one. So one big thing, of course, is the Turing test. In this whole discussion about AI, I'm not going to explain this. An important response to the Turing test was given by Searle. This idea of the Chinese room, and the Chinese room. Everybody knows the Chinese room? Yes. But this is a thing I read later on, which is interesting. This is Dennett's cognitive wheel, and that's, I think, a very useful concept when we talk about human intelligence and artificial intelligence. And Dennett's cognitive wheel was the idea that suppose biologists are interested in movement in nature, and they want to study and understand movement, and they go to the garage and go building things, and then at some point they come out and they have invented the wheel. And the wheel works fantastically. It's a fantastic way to move around, but it doesn't happen in nature. So the whole fact that you build something that actually does the task, so back to the Turing task, might be completely uninformative about how movement in nature really works. And then it called this the cognitive wheel. I use this picture from Escher to find actually the wheel in nature, according in Escher's world. In Dutch, it's called the wenteltation. So this Dennett cognitive wheel will be an important point later in my talk. Now already we move to a bit of psychology. And there are quite some misunderstandings about this concept of intelligence that I like to talk about shortly. And within psychology, if you talk about intelligence, then immediately you can end up in two different worlds. So one world is this world, the world of cognitive psychology, which is cognitive neuroscience, brain cognition, cognitive memory. And the other world is actually the world of intelligence. And both talk about the same thing, apparently. They both talk about what is intelligence, and how should we study it. But there are completely different worlds in psychology, and it's important to understand this. And it was very well explained by a guy called Kronbach, famous psychologist. And he wrote this paper already a long time ago, 1957. And he says that there are actually two types of psychology. And one type is interested in mechanisms. How do things work? And another type of psychology is interested in individual differences. And you can actually do this by two questions about any behavior what you can think of. You can always ask two questions. How does X work? And why do people differ in X? And for X, you can fill in anything. You can fill in arithmetic. So how do people, you can ask, how do people do 7 times 7 in their head? What really happens in the workspace? What's said? That's actually the line of work that Melanie was talking about, how this actually is done. What's the mechanism? You can also ask, why are some people doing better in arithmetic than others? So what actually explains the individual differences? Now, a large part of psychology is about this second question. And you can ask this for any type of question. This is actually an example from chess. So also in chess, you can you see this immediately. If you look at the whole literature on chess psychology, you see that one part is about what really happens. Yes, sir.
Which is which? Like cognition with the differences or the mechanism?
The cognition is the mechanisms. And the intelligence is mostly associated with the individual differences. It's also called differential psychology. And so here you can, you can ask the Groot, who started had this dissertation about chess, was really interested in mechanism. So he was thinking, his question was, how can it that people play chess? What's happening in people's heads when they play chess? And then he was not interested in individual differences at all. He just wanted to know how the average human can do chess or can do any thought processes. How does that work? What's the mechanism? And that's also how it relates to AI, because always in AI, we try to build mechanisms to do these things and hopefully learn something about how this works. In people, you can do recall experiments, eye movement studies. These are studies where you see where people look over the chessboard to understand what's really happening when people play chess. And the completely different question is, how do people differ in playing chess? Why is this the case? Is this talent? Is it nature, nurture? This is about, that's a big discussion, of course, psychology. It's also about the sex difference discussion in chess. Why do women score are lower in the rankings than men? How can we explain this type of differences, which actually seems to be largely due to interest differences? The number of women that play chess is a small fraction compared to men. But that is this world. So there are totally different worlds. There are also completely different people doing these studies, different journals, different conferences. And I guess most people that sit here think about intelligence in this way, but it's very good to know that this other world does exist, and that many associations we have with intelligence are based on individual difference research. I say a little bit about this individual difference research. In this research, the main observation is something that we call the positive manifold. And the positive manifold is basically that if you have different subtests of intelligence, they all correlate. So we are all smart people here. So if you score well on one test, you probably also score on completely different tests. Then you might for yourself think that your strengths and your weaknesses, but overall in the whole population, you're good in everything. It's good for us. And if you look at in the population and you take all the subtests and compute the correlations, then this is the average correlation is about 0.5. And that's a very well replicated finding in psychology. So a big question is, how do we explain this positive manifold? That's the biggest challenge here. And the classical explanation in psychology is the G theory, or general intelligence theory. So this means that people have the idea that there is something in the brain, a G factor, something like that. That's a common cause explanation. So you score well on all these tests because you have general intelligence. And this is the G factor that's shown there on the top. This is a very sensitive thing, because this G theory immediately has something biological, genetic in it. So why do you score well? That's just you're born with it. So you get these questions about individual differences. Are they born in? And even our age, our group differences in IQ, are they genetic? And that's of course, and then we go to the discussion of the bell curve and the Flynn effect. And that's a very sensitive discussion. My own take on this is that the individual differences are partly genetic, but the group differences aren't. But until today, this is a huge discussion, and this makes the whole research in intelligence very political and sensitive. Our own take of it, our own work on this is actually putting an alternative for the G theory together. So this G theory has been the main theory because there was no real alternative. The whole reasoning was that if you have a G factor, then you will have a positive manifold. We have a positive manifold, so there is a G, which is a valid reasoning when there is no alternative explanation. We propose a mutualistic type of model. That's actually a model taken from mathematical biology, where there is a complex dynamical system that develops over time, and there are reciprocal effects between different subsystems in the cognitive systems. And then you can actually see easily that you also get this positive manifold, which gives a completely alternative explanation for this positive manifold, which is less genetic and biological. That's one of our biggest line of research, actually. You need only very weak transfer effects in these systems to get this positive manifold. And this whole approach, this network approach in psychology has become a major research line recently. But back to mechanisms, because that's more the core of the discussion. And if you also look back to in psychology, history of psychology, then a big thing is this what's called the cognitive revolution. The cognitive revolution was about the magical number 7, the interest in problem solving. That all was a response or reaction to what's called behaviorism, which was the big line before that. And many people from very different disciplines contributed to this cognitive revolution. Yes.
What is the magical number 7?
The magical number 7 is that your working memory has about 7 independent spaces. Plus or minus 2. Yeah. Yes. This line of research, so understanding what really happens in the head, it started with this work of de Groot in chess, that actually is intertwined with this whole start of AI. So a lot of early AI was related. Actually, Turing already wrote a chess program in that time, and these chess programs are really based on how people think. So they try to imitate the reasoning processes of good chess players at that time. And also already in that time, you had this discussion about what's true intelligence. And I will give my definition now before I go on with this short history. And of course, that's not an easy question because intelligence is used in very different fields. But I think emerging from lots of literature is this simple definition. It's the ability to deal with difficult and novel problems. So that's two important parts. They should be difficult, I'll come back to that, and they should be novel. And this novelty is a big issue, of course, because as we discussed earlier in the talk with Melanie, there's always a big question how novel problems are for these modern systems, because they've seen it all. Actually, the definition is very close to the definition of creativity. And essential for me is this idea of adaptivity. So the most general aspect of intelligence is kind of adaptivity. And I like to put it on 3 time scales to get it clear. So one level of adaptivity is evolutionary adaptivity on a very slow time scale. And actually that can lead to very smart behavior, like the cuckoo nest, and many other examples in biology where you say, okay, this is extremely smart behavior, but it evolved over many generations. So it's adaptive, it's smart, but it's very slow process. It's evolutionary time. The second level of adaptivity, which is very important, has to do with operant conditioning and classical conditioning. And that is still slow. That's how a dog learns certain tricks, how pigeons learn certain things. And that's based on the Skinner box is a famous example. So that's adaptivity within the life course of one organism. So that's much faster than this one. But there is another level of adaptivity, and that's only seen really in humans. That's really fast, and that's what we call problem solving. So that's an important distinction, that if you talk about this adaptivity, on what time scale it actually happens. And the most interesting one, and the most intelligent one, is the one of this fast time scales where it can happen actually in seconds.
So there probably will be another layer, like super fast, like intuition with the space that we already super well known.
I would put that on the fast, but that's a bit of a, yeah, super fast, yes, yeah, yes.
Could you as an example, or do you use any type of involved?
Yeah.
Because actually the cuckoo is an interesting case.
Oh yeah.
The cuckoo is up.
Yeah. Yeah.
Nonetheless, it knows cuckoo. And
Yeah.
learns cuckoo.
Yeah.
Learns it somehow knows at some point the call for cuckoo, whereas its parents are not cuckoo. So that's why I'm,
No, okay. I feel the problem, yes. Yeah. Okay, but it's actually a mix maybe of the two levels. Yeah. But overall, you see this effect that some things we think in nature that's extremely smart, and it is smart, but it happens over many generations. Okay. So for me, intelligence is adaptation at the fastest time scale, and I'll come back to that in the end. Okay. Now I like to sketch a little bit the history of AI, which is of course impossible, but it's good to have a common language here. One important thing is that we like to talk about this AI winter. So I guess most of you heard about these terms. My interest in AI was born in this winter, which was a very bad start, of course. I will show this a bit in terms of the history of chess and AI. There are many storylines, of course, but this line is one of my favorites. I will talk about this one. And of course, the interest in chess, it's another fruit fly. There are many fruit flies in AI, but the chess is a famous one. And it started indeed with this idea that if we could build a chess computer, this was this 1950s idea, then actually we solved the question of Ade de Groot, how people play chess. That was the initial ideas. And that was completely unsuccessful. So the first chess programs were really weak, and they didn't work. And one thing that people actually really realized at that point, chess is difficult. And now I will say a little bit about what is actually difficult. Why is chess difficult? There are two aspects to this. One is actually this explosion of possibilities that you all can easily understand. But the other thing that's actually, and that's thing that people are really good in, good chess players are good in, is the assessment of a situation. So whenever you have something on the board, it totally depends, of course, on your chess ability. But if you have a grandmaster, they only need less than a second to have a really advanced assessment of a situation. And that can be very complicated to say what's actually happening here in this situation. And so these two aspects I will come back to. The first one is a bit more about this difficulty. And the interesting thing is that the most difficult problems we have in computer science are these problems that we call NP-complete, or actually NP-complete is a subset. And these are ones where you have these trees that actually explode, so that the search space becomes quickly gigantic. But if you have a solution, checking the solution is actually very fast. And actually, I don't know what you know about chess, but chess is a good example. So if you have these chess puzzles like mate in 3 are typical NP-complete problems. Finding the solution can be very hard, but if I tell you the solution, checking that it is a good solution can actually be done very quickly. And that happens in all these problems, and these are all kinds of examples like graph coloring, the trapezoidal problems, Sudokus. They're all of these problems, and I think it's still this 1 million. You can still win $1 million if you solve one, and if you solve one, you solved all. If I understood this whole world well, which is I think 1 billion would be still 1 million is a bit of a joke nowadays, because this is really extremely hard to solve. And in computer science, there are tons of ways to have suboptimal solutions for this. But one interesting question is actually how people deal with this, and also deal with this playing chess problem. And what we know about this is not a lot. It's still a mystery how people play chess. But creativity plays a big role. This fast adaptation, problem solving. And we study this actually with all kinds of methods, error analysis, eye movements, thinking aloud protocols. That was already done by A.D. de Groot a long time ago. I think the two main findings for now that are important is two things are very clear. We are not able to search trees very deeply. Actually, many grandmaster chess players, in most of the situations, they take decisions without searching the trees, not maybe a few moves, but often even less. And they have these very advanced evaluations of positions. So whenever you give them a chess position, they can quickly assess whether it's better for white or black, and have a whole storyline about what's happening in the situation. So how did AI did this? Actually already the second line of AI research. So the first was this Turing approach, where we try to really rebuild human reasoning, which was not successful. But then the Deep Blue type of things came, and it was based on a few tricks. I will quickly say them, most of you know this. There was in that time a very big advancement in how actually to deal with these trees. So you have to set up these trees, and you have to search these trees. But they found many tricks to do this in an optimal way. So the minimax algorithm was an important one, and then in this algorithm to deal with this explosion, there were all kinds of tricks like alpha beta pruning, and actually much more tricks. And they made it possible to search these trees quite deeply. It was also, of course, hardware improvement at that time. Yeah, now we laugh about the computers they then have, but that time they were already able to search these trees for millions and millions and millions of moves per second. So they could build big trees. Secondly, they chose for very simple evaluation functions, where humans were able to have a very advanced assessment of the situation. Here they just count pieces, basically. So there are rules in chess, the queen is 10 points, rook is 5 points, etc. You just count the pieces, and you take the difference, and you have an assessment, which is really bad from a chess point perspective. But the trick is actually that it is really bad at some level in the tree. But actually, it's a cost-benefit analysis. If you can make a more advanced analysis, but then you would have less time to go deeper in the tree. And it turns out here that going deeper in the tree brings more than having an advanced analysis of the ending situation. And tips 3 and 4 were also important. One thing is, in chess you have chess openings. As a chess player, it's very hard. A big thing is actually to memorize all chess openings, which is huge and which is very simple for computers. So they put the whole chess book, they put in these computers. And actually they have endgame table bases. So the chess tree, if you have simple situations with less than 6 pieces, it is possible to compute the whole tree and have then chess is actually solved for these simple cases. That's also in table bases. So if you played Deep Blue at that time, first you played against an opening book, then you played against this tree search thing, and in the end you played against table bases, which were just perfect. So that was what Garry Kasparov had to deal with when he played Deep Blue in 1997, and he famously lost. The pictures and the videos on YouTube are fantastic to see. This was a big defeat, actually, also for me as a chess player. This was quite a shock, but it happened. So yeah, by using this at that point in time, fantastic hardware infrastructure, Deep Blue with these tricks was able to beat the world champion.
So did Kasparov know about these 3 phases of the game? Because
Yeah.
if I understand correctly, it means that once you're down to 6 pieces, you should give up.
Yeah, or if it's a lost position, of course. Otherwise, not.
Right.
Yeah. There are famous examples where people give up, and actually they should not give up. So yeah. No, actually, there was Kasparov was mad because he said it was unfair. Actually, I forgot why he thought there was some human involvement in the move selections. He said some moves were so human that he could not believe that it was. That was actually the thing. So he was actually thinking that some chess players were involved in actually in the middle game, not in this first part, in this last part. But actually, that was probably not the case. He was just beaten, honestly. Yeah. So chess was solved in the sense that it beat Kasparov, but it was also very disappointing. And now we come back to this Dennett point, because I already told you now how Deep Blue actually worked, and it was totally different from how humans play chess. So this whole idea, okay, let's build a chess system that actually beats the world champion, maybe it solves in that sense the Turing test. It really is Dennett's cognitive wheel. So it really showed exactly how we do not play chess. Everything was different from what humans did. So this is really a case of the cognitive wheel. So that was also disappointing. So I was double disappointed, actually, because this actually didn't learn us anything about the psychology of chess, and actually chess was solved. So that was, Mike.
The paper last year, so they're using different mechanisms to a novice play. Right? So
Yeah.
But even with Deep Blue, it wasn't just a single evidence. Some kind of evaluation of branches and kind of cut off.
Yeah.
So there is an analogy there.
Yes, yes.
First space is somehow constrained by situation.
No, it's because indeed also Deep Blue could not search the whole. It has to stop its search at some point and then use this basic simple evaluation function.
That was the really big advantage.
Yes. Yeah. So it's not totally. Of course, we also have a way to search the trees a little bit, so it's not completely different, but it's largely different. I go here. Use the time. So immediately also the question came up. Yeah, okay, Deep Blue did it, but now the new challenge is actually, can we build a new chess type of system that actually can learn to play chess and has much more human-like and actually can also be the world champion. And that point in the 1990s, there were not much progress in that direction. So people tried, they came to some level of chess playing, but these learning chess programs at that time were really bad. Actually, nobody really believed that it would really happen. Actually, in this winter in the 1990s, we didn't believe that this would happen. We didn't believe self-driving cars, natural language comprehension, all these things that are now all there. If I had to bet at that time, I have lost lots of bottles of wines, because all these things, I was completely convinced it was never going to happen. And this was also for this learning chess type of programs. But of course, current AI, I'm not going to, I just go quickly over here. It's completely changed the last 10, 15 years, and current AI is all about learning. So that is a total revolution. And there are actually two types of major developments here. One is the deep learning neural networks that Melanie was already talking about. And the other one is reinforcement learning. So reinforcement learning is the other big thing. And interestingly, if we think already about my definition of intelligence, this one is really more about classical conditioning. So this learning by examples, many examples. And this is more this operant conditioning that we also have studied in psychology for long words, and this trial and error and learn by reward. And these are really the two pillars of modern AI. Although, of course, there are, let's skip this. I also noticed that this public is quite advanced here. So this is a short overview of what happened in this other line of history, because that's also fascinating. So we had these winters in AI. At the same time, we had many different branches. So we had more this reasoning, symbolic type of AI. We have the neural network approach, we have the reinforcement lines. But all these lines had their winters actually, and some of them quickly aligned. But this is a short summary of this history of the neural networks approach. And this is this reinforcement line that also all these already started early. So the reinforcement learning goes even back to an earlier tradition in psychology, the behavioristic approach, which was 1920s, 1930s already. So they all have long traces back in different sciences. Yeah, this came, and this is also now combined. So this is a very important step. So reinforcement learning first was based on these Q matrices, some of you probably know, but now you have a neural network built in these reinforcement learning systems. So you have deep learning, reinforcement learning. And again, this led to amazing successes. So here are some of these successes. There are actually more, and now keep it simple, deep learning. Neural networks and reinforcement learning, but there are some other very important tricks developed in the last 10, 15 years that have been important here. But all these challenges that I put here, on each of these, in the 90s, I would have put one or more bottles of wine that it would never happen. Now, you might disagree with some of these processes, but in November, I was in US and I was actually driven in a self-driving car, which I really never believed would happen, but it happened. Yeah, if you go, I can tell this story for each of these lines, but let's get back to chess. The revolution in chess, the big quest, can we make these learning programs, that really happened when AlphaZero Chess was published, which was a total shock for the chess world and also for me, actually, both from the scientific point of view and from the chess point of view, because this was a fundamentally new approach. And now we are already used to this, but it was totally shocking. The self-play idea was shocking, that it just played itself for, they claimed 4 hours, but it was on this big infrastructure of Google. If you do this you're on your own, it will take months and months, but okay, it was only based on self-play. It had no opening theory, no endgame table basis. It searches still a lot of moves, but compared to the old Deep Blue type programs, it was almost nothing. Yes.
Bullet points have been around for a
Yeah.
long time.
Yes.
What made this work?
Now, the combination of these things. So, because this Monte Carlo tree search, for instance, also, I'm not have no time to look into to tell more about. This is really a insane, stupid idea, actually. And in itself, it does nothing. But combined with the deep neural networks and the self-play somehow, and the huge hardware, of course, yeah, somehow it gave this power. But if you look at each of these tricks itself, yeah, you don't see how it could be. Yeah. Yes. Yes. But yeah, somehow for a long time, people built these self-learning chess programs and they didn't go anywhere. Yeah, I don't know. But
It's maybe the computation.
sorry?
Maybe the computation.
Yeah, so that's the point of Hinton, of course, in his that always says that everything was already out there. The only thing that really changed was the GPUs, and now we didn't have the time in the machines to wait long enough. In that sense, it might be just computing power. I think there's more to it. It's really also the smart interaction between these systems. I think the Monte Carlo tree search is relatively new here. Overall, okay, good. Yeah, so this was an amazing results, and yeah, there is actually not so much scientific research on AlphaZero, also because, of course, it's not an open system, but this is a great paper in PNAS. where they looked, there's a lot more graphs here, but I skipped most of them, but they really looked in what's happening now in AlphaZero chess. Also over time, you can see how it develops over time and what's happening. So this is one funny thing. This is the opening preference of human players in the history of chess. So for a long time, people only played E4, and then D4 came into business in the 1930s. And now it's a bit of a mixture of different openings plays. And these are different runs of AlphaZero chess in its development. First, you see for a long time, it just does random first moves. But then suddenly there's a point that it gets a preference, first also for E4, then more D4. These are different replications. And you see that, it actually rebuilt all our opening knowledge that we have developed in the chess community by itself. And it came luckily to very often to the same type of conclusions. What's not really mentioned in this paper, but from a complex science perspective, this is very interesting that you have this phase transition here. So if you look at the paper, you also see this in other graphs that at some point in the learning process of AlphaZero chess, things fundamentally change. So for some time it's rather long time random chess. So this might be Mike's point. In our previous time, we had not the power and the money to go behind this point. But this is this magical phase transition where suddenly the sim system starts to play real good chess.
So if I look at the final distribution of opening, it's much more varied for chess zero than for human. Is that because they force it to keep experimenting, or is it really saying it's good to change it up?
I think it's more a human thing here that people are attached to the openings. It's also, if you change as a chess player your opening play, you have to do a lot of study again. So you keep also in this little area because it's hard work to study and to memorize everything. And that's not a problem for this chess computer. I think it's more like this.
Changing the human.
Yeah.
And now the computer use the lot in
Yeah. Yeah.
So they know the opponent or just to.
Yeah.
They make things.
Yeah. Okay.
And what's the difference between the three different panels on the bottom? They almost, so are they different runs where they?
Different runs. If I remember well, it's just different runs. So nothing changed. It's just replications.
So they must have reset the system.
Yeah, they reset it, and there's some randomness in this system, types of systems with this temperature thing. I don't know how they really does it. So it's not there is some randomness in the system, but there's no manipulate. It's not that they manipulate something here. It's really replications of the same learning process. There are many, many different things, of course, that you can choose. So that's another story. I don't go there. But these are replications. But you see in all cases, this phase transition is very clearly there. Actually, it's not mentioned in the paper that there is a phase transition. So I found that fascinating for another reason. But and of course, it's AlphaZero chess is a closed system, but very important is Lida chess zero, because that's a replication as an open source project. Many people work on this, and actually the modern chess competitions where chess computers play against each other, it's always number 1 or 2 now in the rankings. So this system, and there's now a lot known about these systems because they replicated this as an open source system. Given this recent AI breakthroughs and also in chess, but also in all these areas, I'm a much more optimistic person if you think about this relationship between human intelligence and artificial intelligence. They are much more human-like at the implementation level because now they are based on neural networks and reinforcement learnings, which are both also, of course, pillars of human intelligence. The performance is much more close to what humans does, depending on the task, of course. Also including the errors, actually. So that's also fascinating. So one famous discussion in chess is that Lida chess also does can blunder in very human ways. which is a topic in itself. But and I think maybe the most important thing is that these systems learn. So that's the biggest difference between the pre-winter AI and the current approaches. So to come back to the beginning, so we still have these questions now, given this history. What now about understanding? I will say something about it. Fluid intelligence and this fast adaptation. So the first conclusion that we also have in our paper, Claire and me, is that if you only think about crystallized intelligence, and for not psychologists, we make a difference between fluid intelligence and crystallized intelligence. Crystallized is more this applied intelligence that apply to chess or whatever task. It's just astonishing. If you take any crystallized intelligence test nowadays, the large language models, but also other AI models, they just outperform people easily. And sorry? Crystallized intelligence is applied intelligence. So where you have your, the fluid intelligence is your memory, your reasoning capabilities, so the more basic forms that are quite general. And then if you apply these to chess or whatever task, learning a language or so that's the term. And chess is an example. And if you look in chess, so this is a picture of where the chess players are. This is the ELO rating scale. These are beginners. This is the world champion at 2,800. And this is the history to 2000 of the chess computers. And here Deep Blue actually beat Kasparov. So this was just before 2000. And now I do a fantastic interpolation in PowerPoint. I'm really proud about this. But actually, it is spot on because the current estimation of the ELO rating of Lila chess is about 3,600, which is totally amazing, because we have the human distribution and then we have a long time nothing, and then we get these current chess computers. So they are really amazingly good, and actually it's quite linear on this line. And one latest, I've just found this out a week ago. The latest, because this difference is so huge that it's actually hard to explain how much better they actually are. But one way to show this is the Lila Queen odds bot. So these online chess systems like Lichess and chess.com, they now have a bot, and that you can play that Lila chess, but it has no queen. And then you can try to beat it. And it's now 10-0 for Lila against Han. I cannot beat it, and I'm an average. I'm here. I'm at the middle of the distribution of human chess players. I heard grandmasters can do this, but then if you do this, you can do the rook odds. So you have Lila has no rook, or you can the knight odds. The grandmasters play the rook or knight odds, but they have a hard time winning this game. So. But there's another interesting thing here. So this sounds just like, okay, chess is really done. But then you have this. So I don't know who can play a bit of chess here, but look at this one is the easy one. So who's better here?
The black one.
Sorry?
The black.
Yeah, you are not a chess player. Any chess players here? Okay, if you are an average chess player like me. No, so there's no way black can actually pass this wall. If you are an average chess player, you see such a thing in half a second. So in half a second, we say, okay, this is a draw. There's no way. And this is called an anti-computer position, because computers in the past, but also the fastest, best computers that are out there, they don't get this. If I give this to Lila Chess or Stockfish or all these programs, there's a rule in chess that says that if you, for 50 moves, you cannot take a pawn or give check, it's a draw. And I tried this with one of these programs, and it goes really the whole tree. And it takes an hour or so on my computer until it's at move 51, and then it says it's a draw. And all this time, it doesn't realize, and humans, and this is one that was invented by Penrose. But there are many of these examples of anti-computer positions where, and then we get into this discussion about understanding, because we would say, human chess players just immediately understand there is no way to win, and leader cannot do it.
When you test it, you initialize the program with this.
Yeah.
But would it naturally be there from starting from again?
Now, these are very rare positions, of course, but there are examples in real chess games where this happens, but they are quite, this is so, these are very chess, you need a lot of chess knowledge to understand these, so this one is actually very simple, but they are rare, but it can happen. Actually, I asked O3 yesterday what he thought about it, and they didn't agree. It says the pawn lock is only an illusion of safety. It's not an illusion, it's real. But actually, it's really nice to, if you give the LLMs chess position, it's really funny what's happening, because sometimes they guess a move correctly, but the reasoning, the argument, what they have this whole story why this actually could move. It's total nonsense in all the cases. So adding these types of putting these things in LLMs is quite funny. Yeah.
We have rendering fire that we can destroy our own unit.
Yeah.
The black ones are better.
Yes. But we can't. But then it would, yes. So now we go back to philosophy a bit. Does Alpha Zero understand chess? And I'm running a bit out of time, but I only want to make one little point here, 2 points here on this slide. So one thing is that as a psychologist, what I saw is that when we talk about this Searle experiment, in this case, it really gets a binary thing. So either you understand things or you don't understand things. And computers clearly fail Searle's test, so they do not have understanding. And also in chess, we show this anti-computer position and says, it's all great that it can play chess, but in the end, it doesn't understand chess. But if you talk about humans, understanding in psychology is often a very gradual thing. It can be jumps or whatever, but there are many different levels of understanding. If you talk about zero, for instance, we have a lot of physicists here, mathematicians, who really claims to understand zero here in the room? No hands. Do you understand zero?
On its own or with interaction with other things?
Yeah, there you go. So there's a whole gradation of course, a child understands zero to some degree. It's nothing. I have no money or no cookies. That's zero. But also actually in our teaching, if I'm a psychologist, we teach the t-test, for instance, statistics. Or students have very different levels of understanding. So sometimes they know to press what button in what computer program. They understand the output. They can implement it themselves. They can understand the mathematical derivation. So there are many different gradations of understanding. I think it's necessary to do this also when we talk about AI. To make it a binary thing is strange. And if we don't make it a binary thing, it's clear that there's a lot of understanding or intelligence in these types of systems. But there's more to this. And on this point, I have a completely unstable position. So when Abel asked me for this talk, I thought, I know what I think. But yesterday evening, I think, I don't know what I think. And because there's also a discussion, I think, for Searle and Dreyfus and many other philosophers. This was not only, for understanding was also about meaning, feelings, having goals. And that's totally out of the picture. So if you think about understanding from a cognitive point of view, there might be quite some understanding in these systems. But if you think about goals, meaning, then it's very far apart. And a very simple way to think about it, that was another thing that I noticed, that when AlphaZero came out, it had these fantastic moves. And the whole chess world admired these moves as brilliant moves. But to say that AlphaZero also enjoys that it now had a brilliant move, that's quite an odd question. That's clearly not happening. And that type of enjoyment, which relates to feelings, is probably an essential part of understanding that's completely out of scope currently, and maybe for the better. I want to be, I'm not sure what the other speakers are going to talk about, but one of the tasks that was not mentioned by Melody as an example of analogical reasoning that's very famous and very interesting that we study, that's actually Claire and Melody and I am writing a paper on, are the Bongar problems. And that's also put forward by Hofstadter in his book, already mentioned. And he said that Bongar problems lie very close to the core of pure intelligence. And these tasks are fascinating. And these tasks are like this. So you have 6 figures here, 6 figures there. And your task is to verbalize what is the difference between the 6 on the left and the 6 on the right. And you can make many different tasks here. And one example, so Bongar, who created this, when he made a list, and there's also a big list now on the internet. And we created a lot more. Actually, Claire created them, and we also have a child-friendly test. And we now compare how people do the very similar line as Melody was doing with the letter strings. And the other people were doing with the matrices. We do this with Bongar problems. And here also, the AI systems really perform badly. And here they even perform more bad than 10 children, if I remember well. Equal to children. Yeah, some of the versions do equal to children, but score way lower than adults. So this challenge, which was put forward by also already in 97, so that's really nice, is still very spot on. It's really one of the biggest challenge for current AI to solve. And in our expert workshop on Monday, I don't know whether there's still spots free, talk to Claire, we will present some work on this. Go back to this point. I think I already said this point. So I made this point in the beginning that true intelligence is about fast adaptation. If you think about current AI, the big tricks, neural networks and reinforcement learning are about this slow time scale. It's learning by example and it's learning by trial and error. So it's still not at that level of fast intelligence or fast adaptation. People are trying this. That's one term in AI that's very popular now is one-shot learning, where they try to develop methods to really do one-shot learning. It's very hard to assess how successful this is. There's an explosion of literature in AI. I don't know what your assessment here is. What I read about it, it's still in its initial states.
Yeah, I mean, depends on which benchmarks you.
Yeah. But of course, this is one of the biggest challenges to go one step deeper and to bring AI to this level of this fast type of adaptivity. Okay, summary. So for me, intelligence is about solving hard and novel problems on the fast time scale, and that's still not what we do in AI. Current AI models are constructed and operate in ways that are much more psychological plausible. And the whole interaction between the study of the human problem-solving abilities and AI abilities is very promising in my view. But there are still problems with novelty and understanding. The current methods are mostly based on the slow timescale adaptivity. We have this issue of anti-computer positions, the Bongar problems, and also other problems that were put forward by Melanie. I made this point that understanding should be seen as a gradual thing when we judge AI, because we do this also in humans. But compared to understanding, feelings and goal-directed behavior remain even more elusive than cognitive understanding. And the last point is study your chess. Thank you.
Dig a bit deeper into this.
Okay, you first and then you. Yeah. Yeah.
Firstly, thank you for the I want to dig in a bit more into this, into your interpretation of the time scales with respect to AI systems. So a couple of interrelated questions. One is, do humans get better at these kinds of tasks over time? Can they get better? And in that case, if they do, would you
not consider that to also be some kind of slower time scale than
Yeah.
fast time scale?
Yeah, it's a difficult discussion. So humans, to some degree, they can generalize and transfer things relatively easily, but there is also a transfer problem in humans. So even in children, actually in teaching, teachers are always disappointed in the transfer children make. So you learn them some trick in mathematics and then they have to apply it in the next physics class and they don't see the analogy. So also for humans to do what we call this far transfer. So we are good in near transfer. Far transfer is an issue. And this can also be developed over time. So you're completely right. So this transferring this type of fast problem solving ability and expertise you can build up in one domain is also limited, and there's also a slower learning process in this generalization process. That's a good point, yes.
So, and analogously, in AI, we have a learning phase, but not a deployment phase. Of course, the learning phase is quite slow.
Yeah.
But the deployment phase in adapting to the current situation, for example, with the market research and with the reinforcement learning, evaluating the states, that seems to be on the faster in this character.
Yeah. No, I see. Yeah, now, of course, I'm hopeful, guys. So I really hope that we can make this step from this reinforcement learning neural network approach and build in these more faster learning steps. But yeah, we have to see. But
Actually, very similar questions about the separation time security and
yeah,
the focus that you put on learning for AI system. But for human beings, it's the same thing. Like a chess grandmaster is only good in the fast time skills because he studied his whole life and learned the game.
Yeah.
So these things tie into each other. Maybe just going to follow up on that. Are there any models for that? Or the way you can formalize it?
So more meta models that describe this interaction of these levels. I guess so, but more in an abstract sense. So you have, of course, dynamical system models with different times, adaptive, where there is adaptation, and then you can study the interaction of time scales. So this is an existing thing, but I know this more from the field of biology. But I don't know how this has been applied to this AI type of learning. That might be an idea, yeah.
Sounds like the difference between intelligence being good reasoning versus good intuition.
Yeah.
Somehow, because you're saying that sort of the big breakthrough was when they realized with test computers, you don't have to reason through everything, you just need to build a good intuition, and then you get away with little reason. Yeah,
that's I find also very confusing. I have a completely unstable position on this. So to go back, Ade de Groot, who started this research in his last phase of his life, he gave many talks about intuition. So he said, yeah, all this problem solving, reasoning, it's really about intuition. Chess players have intuition. And I went to his talk as a young student and I was completely unclear what he meant with intuition. And actually, it's still unclear. But you can say that sometimes what you now see in these neural networks, that is because what they now also can do in Lila chess is actually let it play without any tree. So now it's a combination of tree search and neural networks, but you can also say to Lila chess, no search. It's only, there's no search at all. It's only the first, and that's just amazing how well that already works. Yeah, you could say this purely associative direct reaction to the chess position. That's intuition, which then it's easily solved, certainly. But you can now ask a new question and I'm confused again. So intuition for me, I don't know. There's something interesting here, but I don't know to get concrete about it. Yeah.
Your ignorance are find intuition as having heuristics.
Yeah.
You know, some kind of scary quick rules.
Yeah.
And I think there's now a lot of evidence that the machines, they also, well, there are more specific heuristics about its
Yeah.
that they've learned a lot of very, not completely generalizable heuristics, and that's maybe why they have trouble generalizing to the opposite.
Yeah. Yeah. Yes. Okay. Sorry, I have to. Yes, Monte Carlo tree search.
Essentially, not just a random walk on the tree, but directional.
Yeah. No, it's not MCMC, it's the Monte Carlo tree search. I think that's something different. Yeah. Yeah. It could be. I'm not sure, but something like that. I think you also refer to this phase transition, because there the Monte Carlo tree search program is used. So somehow. Yeah, I think these are. I think they're different things. I'm not sure. I think. Okay, but anyway, whether we have the same meaning for that, I still don't know the answer. So, but okay, I don't have an answer on that. Yeah.
Smart enough to understand how to work. And if I look at this, then I think that is that all in the extremely slow for us? So does that mean that the whole concept of embodiment is not part of intelligence?
No, to me, it really has to do with this point of show and drive is what they could have. There is something to understanding more than just being able to play chess or solve, even if it solved all the problems that Melanie put on the board, and even if it solved the Bongard problems, it's still clear that there is something missing in terms of meaning and feelings, and that has something to do with embodiment and the fact that we come from an evolutionary process, that we are living systems. These are, of course, not living systems. So there is a whole discussion. I think someone should give a whole new talk about this aspect, and I'm not expert in this, but it's clearly that even if we have solved all these tasks now with the new generation of AI, that the last word is not said about understanding meaning and goal-directed behavior and embodiment. So some people think we need to put all these systems in self-replicating robots. And as soon as you have self-replicating robots, which is the hard thing, and build in, and then all build this in AI, then we may come to this level of a way of understanding. And actually, probably nobody wants to go in that direction. That would be quite a dangerous world, probably. But I'm not an expert in that discussion. Maybe you have something to no.
Well, it may be that embodiment is kind of like shortcut to learning, that we have not only embodiment, but we also have kind of drive to understand the world causally, being able to do things on the world and to actively learn. Which makes it a lot easier to learn. Whereas they have to have, you know, they
Lunch, I think.
I want.
Oh, no. I take your role.
I can take it. You have a pretty, you have a definition of intelligence. You saw that one?
Yeah.
I was just wondering, has the recent use of AI changed your definition? Or has it,
Now the realization that these time scales, that's my newest way to, because the difficulty and novelty, that's already for a long time there. But then I realized that there is something to human intelligence in terms of these time scales, in comparison to what now, because most of AI is not, it's again a simplification, but most of it is about reinforcement learning and neural networks and combination. And that's what we in psychology would call a classical and operant conditioning, and they are both on this slower time scale. Of course, they go really fast because the computers are fast, but in terms of the number of examples they see of trial and error, it's still a slow process. And I also see we should not overstate how smart people are, and they have huge problems with problem solving, but still also what Melanie showed in the beginning, or flexibility and or ability to do far transfer is still on a different level in that respect. So it sharpened my definition a bit, and I think this time scale is a new way to think about it.
so it needed 20 books to conclude the later done.
Yeah.
That's not fast.
No.
That's slow.
No, it's still slow. Yeah.